Hello, welcome back to Chapter 5, Section 6, where we are learning about the quadratic formula. In this problem, I'm going to read the problem in a second, but in this problem, we have looks like a helicopter, and it has some water, water. Could also be like a flame retardant. This helicopter is trying to put out a fire. Very, very real problem, particularly when you talk about the fires that have been on the West Coast, and also like earlier. I'm filming this in late 2020, so if you go back to early 2020, there were some devastating fires in Australia. Out of control fires in forests are very difficult, to put it mildly. So one of the things that comes up is, well, are the pilots actually doing this calculation before they take off? Or are they doing it on the fly, literally on the fly? And the answer is probably no. All these calculations were performed before anything actually happened. However, there are sometimes things that change the plan that do mean that pilots or the crew of the aircraft have to adjust for, and they have to do that. One of my hobbies, one of the things that I'm interested in is aviation, particularly military aviation, and I was reading about, and I don't want to get into the issues of war, but I was reading about a situation where something had happened to the plan for some like a squadron of bombers, and one of the pilots had to quickly recalculate in order to make the adjustment, and the calculation would have involved this, except there's probably more variables. Okay, so it's not just high school algebra that's being considered, but also maybe even some more variables. But it's very simplest form. The timing was different from what they were expecting, so they had to do some changes in the recalculation, like quickly, as they were trying to attack a target. All right. So the answer is yes and no. Sometimes things are all planned out, things are all done automatically. Today's aircraft are usually equipped with some sophisticated computers that can probably run these calculations easily. But the truth is that someone had to program it. So instead of it just being, I don't know, I punched the numbers into the computer and I got an answer out, sometimes you need to be able to know how to do it by hand, particularly if it's something very, very, very important. Again, I don't want to get into the politics or the morality of war, but if an airplane is trying to destroy a particular target, you certainly don't. No one wants the weapon to be off course. So it's very, very important that people double check this, is what I'm trying to say. All right, so let me explain what's happening here. We have a helicopter. Helicopter's flying this way. Now, there's two things that are going to happen, and this is why it'd be great if you guys had a little physics as a background, but most of you are not going to get that until next year or the year after. When the helicopter pilot releases this bucket of water, and it's really cool, you should watch this. Sometimes these helicopters, or even like the planes, they'll fly down to a lake, they'll scoop stuff up, and then they'll do this. It's going to be flying forward. Two things are going to affect how this is going to drop. First of all is going to be gravity. Now, the formula, so to speak, for gravity is a quadratic, because you have the acceleration due to gravity. That means that, and we talked about this earlier, is that means that the path that something that's going to be dropped is going to follow quadratic. But I've got another factor. Since the helicopter is moving forward at the time, not only is it going to fall down, but it's not going to fall straight down, okay? There's also going to be a force that's going to push it forward. So the path of this is going to follow that part of that parabola. Now, we've already done all the modeling for you. So the height, just the height part, is going to be y equals negative 16 t to the second power subtract 2t plus 500. Now, that's not make-believe. The negative 16, the negative tells me that I'm going to have a parabola that's upside down, if you remember that from the 5-1, which is going to be going to show me that gravity is going to pull it down. That's where the negative comes from. 16 is half of the acceleration due to gravity, so this is based upon 32 feet per second on Earth. The negative 2 probably means that there's going to be a slight push down of 2 feet per second. So it's going to be pushed down. It's not just going to be let go. The 500 actually tells me the height of the helicopter, or actually the height of the bucket of water specifically, when it's released. So it has to fall a total of 500 feet. What does T stand for? T stands for the time after the helicopter releases it. T equals 0. If T equals 0, then that means that the height is at 500. That's instantaneously before you drop the bucket. The pilot drops the bucket. And Y, I don't like the fact that they use Y. I think it would have been a little bit more specific to actually use H for height. But that's just going to be the height of the bucket. All right, so we got all that out of the way. All right, the next question is going to be the horizontal distance from its point of release is modeled by this, 91t. What that tells me is that for 1 second, the plane is going to travel 91 feet. The helicopter is going to travel 91 feet. So we don't have to do it. We can convert that to miles per hour. That's something we could do, but it's not necessary. All right. We just know that the horizontal distance from here to here is going to be 91 multiplied by each second. So it's traveling at a constant rate. That's why it's a linear function. All right, so we got to do two things. We got to figure out the time that it takes for the bucket of water, to fall and hit the ground. In other words, when is this going to be 0? So the height is going to be 0. And after we find the time for it to hit the ground, then I'm going to figure out, well, how far away does the helicopter have to be from the fire in order to hit the ground at the fire, so I can know, so the pilot will know when to let go. All right, so first I got to solve this for t. This is a quadratic, and because these numbers are going to be a little difficult. My parameters, my a is negative 16, my b is negative 2, and my c is 500. Yikes. But we're going to do the same thing that we did for all the other problems, right? And for this, I just need more space. So I will try, I'll tell you what, I'll just put this piece of paper in here and I'll just grab this when I need it. So from what I just wrote, my a is negative 16, my b is negative 2, and my c is 500. So let's figure out the discriminant first. B to the second power minus 4 times a times c. This is negative 2 to the second power, subtract 4 times negative 16 times 500. All right. Most of the time we're able to do these in our head. You could probably do this in your head if you wanted to. I'm going to cheat. So I know negative 2 times negative 2 is positive 4. Negative times negative is a positive, so I know I'm going to end up positive, which is nice because I'm going to get real solutions. 4 times 16 times 500 equals 32,000. And I can add these in my head. I get 32,004. All right, that's nice. Now let's put this into my quadratic formula. Quadratic formula is x equals negative b plus or minus the square root of what I just figured out divided by 2a. My b is still negative 2, so I get the opposite of negative 2. My discriminant is still 32,004. And my a is still negative 16, so I got 2, negative 16. All right, don't panic. One of the things about these problems that are really based on reality is that they look difficult, but they're basically the same as what we've already done. I got to find the opposite of that, take the square root of that, multiply that. So the opposite of negative 2 is 2. The square root of 32,004, yeah, that's a huge number. But in this case, we really want to find the actual time. So I'm going to take this, and I'm going to do it on the calculator. And of course, I'm going to just estimate it a little bit. Let's say 0.9. And then 2 times negative 16 is negative 32. Okay, now what do I do with this? So remember, I get 2 answers. I'm going to put it up here now because I'm running out of space. I get 2 plus, and I could go ahead and use this, but it's okay. I'm just estimating. 178.9, and I'm going to divide that by negative 32. So one of my solutions, oh, I am so sorry, I messed something up. I didn't even catch it. I'm not using x, I'm using t. Duh. Okay, t for time. So one of my solutions is t equals negative 5.65 seconds. Now you're probably thinking, well, that doesn't make sense, and you're right. So let's try the other one. My other solution is to subtract 178.9, and then I divide that by negative 32. Excuse me. And my other solution is 5.53 seconds. Now remember, time cannot be negative. So I have to use 5.53 seconds. Now you're probably wondering, well, if time cannot be negative, why did I get a negative? That's because, going back to this function right here, this function does not know that it is part of a real problem. This function, if I graphed it, would have another branch, another side of the parabola over here. Okay, so basically, if there was a way of thinking about it with like the bucket of water, following the path of this function, in other words, going up to the helicopter, I keep saying plane, going up to the helicopter and coming down, then this point right here where you're going to drop it would be another 5.65 seconds away. Okay, but you don't have to worry about that. So, at exactly 5.53 seconds, that's how precise you have to be. That's how long it's going to take for the bucket of water to fall from the plane. But I need to know if the helicopter is moving forward. I need to know where the helicopter needs to be in order for it to actually hit it. Because if you're too far away, the water's going to land here. It's not going to be in the fire. Or the picture doesn't show it, but if the fire's just here and there's nothing over here, you might overshoot it a little bit. So I'm going to use this, x equals 91t. So for the horizontal distance, I get x equals 91 times t, t being set for seconds. And what this probably means is that the helicopter is moving 91 feet per second, which is pretty fast actually. So all I do is I take that answer, and I know I've got a rounding error. Okay, I can go ahead and just do this, say times 91. All right. I can also do 5.53 times 91. And they're slightly different. So this is where it's important that we try to be aware of our rounding errors. And that if you round off an answer earlier in the problem, then that rounding error is going to, if you keep rounding off and keep rounding off, the error is just going to get out of control. So we have to be mindful of that. But probably, let's just do this one. Hang on a second. Yeah, I'm okay. So I'm going to get 91 times 5.53, knowing that there could be a rounding error. That means that the horizontal distance is going to be about 503.23 feet. So if I go back to my picture, from here to here, the excuse me, the helicopter needs to be about 503 feet away. 0.23 feet, that really comes down to 3 inches. That's a quarter of a foot, which is 3 inches. So you're never going to have a perfect measurement, but again, we don't want to compound our rounding errors. All right, we'll see you in the practice problems.